Welcome to the verification session, the second to last session for two great talks. The first one is going to be delivered by Klaus Gleissenthall. Cardinalities and universal quantifiers for verifying parameterized systems.
Thanks for the introduction. Okay, so parallel and distributed systems, and these systems occur in so for example as consensus protocols, then as synchronization primitives on. Okay, so and this talks about verifying them, and so for that let me so the sort of arguments, the correctness arguments that you need. Okay, so let me start off with the consensus protocol. So, and each one has an issue wants to achieve is that all the nodes agree on one of the initially proposed values. Okay, and the way that most of these did is that they try to form a majority. So each process tries to be inside of a majority. Okay, so if you have three nodes here, and okay, agreed or are inside of a majority W, then what in fact you can conclude is that they V and W they agreed on the same reasoning that happens in these sort of protocols. Okay, so now actually plays out in a full. In this protocol, you have 4 nodes. That given an initial value there. Try to agree, and the way they do it, the nodes, each node broadcasts its value to the others. Depending on the value, they're going to update their own value. Is that messages are lost over the channels. So we don't have Byzantine. Okay. Now, rules by which the nodes decide how to update their values. The first one is so more than 2/3 of the processes, and here from is you receive. Then you choose the value that was most often. So the second one is the second rule by which they update their value. 2/3 of nodes that you heard from share your value, then you decide on that value. Okay. So okay, so everybody broadcasts their value, but the right downside is cut off from communication. So okay. So let's look at node 1. So it can apply the first rule, since 3 is the most often received value. 3. Okay, so next round, same thing, same node. And now, since they can apply all the 3 nodes that are basically by the second rule and decide on value 3. Okay. Okay. So now, what do we want to verify about this protocol? Verify that a property called agreement, P and P prime, if P decides on a value V, W, then actually they must have decided on the same value. Okay. The invariant that you need in order to prove this. So for all, if P decides on a value V, then actually the whose candidate value is also that particular V. Okay. about this invariant. So first of all, application. And the number of processes that these processes are supposed to run on cannot be determined a priori. So you cannot say, oh, this is only going to run 3 or 5. Enumerate all nodes in the network, but actually whatever that number is. Okay. So second of all, this invariant cardinality, namely the number of nodes that share your value v. And okay, so the way this this is, so if you have two values, two nodes decided, then each of them is in a majority, and by that they have to have the same value. Okay, so what's to say is, okay, if you want to verify cardinalities, okay, so let me of a protocol and the kind of reasoning you need to do. This is a locking protocol called filter lock, and you in levels 0 to n-1. And what they want to do is they want to proceed to level n-1, which is the critical section. Now, so first, thread can go ahead if there's no other to the top. And the second one, it can know there's some other thread at the current level. So say we have 3 threads, and the leftmost thread tries to go into the critical section. So you can just okay. Say the second one tries to. So then now you can apply the second rule, since there's someone else at level 0 can go on to stuck because none of the 2 rules apply. Okay. Yields and goes back to level 0, then again it can go ahead. Okay, so the property we want to prove about that is processes at level n-1. So in the critical section is bounded by 1. So okay. And that you need to prove this. So for all level 1, the number of threads that are at that given level is bounded by n-L. Okay. Again, this invariant contains a cardinality. The set of all threads that are at my level or at a high level, or at level L or at a high level. So again, this and what that basically means is that cardinality, but basically you track one cardinality for each level. Okay. So here's how that actually proves mutual exclusion. So you have L, you have n-L threads, so you have then one less at level 1, and so on, and this one, which gives you mutual exclusion. Because, well, the first rule obviously does, and so in order to advance, there needs to be which stays there and has to wait basically at the next level. Okay, so sort of arguments that we need to find, and okay, we want to verify. What do we do if you want to verify a program and get proof? Program verifier and just let it run. So these are contestants in the software verification condition these are these sort of categories. There's arrays, but somehow there's no mention of cardinalities. The problems I showed you before. Okay. I'm going to show you a method called Sharpie that can find these sort of invariant. In particular, the two I showed you before. And so now I'm going to, the biggest questions are, in order to synthesize, to come up with invariants, the biggest question is how to choose what to count. So we don't the description of what you want to count as an input, but actually our method. And second, the question is how to go about the counting. And I'm going to show you how this works on a very simple example. We have a bunch of threads, and we're going to increment A. Okay. We want to prove a very simple property, saying that if there's one thread that has bigger than 0. Okay. So what we do in our method is encode this. So, for example, the initial states of that. So initially, all threads are location 1. So local variables are functioned from thread. Okay. So this is a transition particular thread me that's going to make a move, and what's going to do is going to update its program counter to 2, PC prime, which is the variable after, and so the function is the same as PC except for position me, where it's, and similarly A is incremented. There's some thread me at position 2, and this implies. Then, given these, given this logical formulation of the program, we pose constraints on it to satisfy the property. Okay, we say, find me an invariant. The invariant holds. If the invariant holds and you take a step, then and finally, the invariant needs to be strong to prove the safety property. Okay. Now, to our solver, then it gives us back this solution. The number of processes that bigger or equal the number that have already incremented their counter. Okay, so some questions were how to choose what to count, and so I'm going to start off with how to do the counting. And these are application conditions where basically the invariant is plugged in, and you want to just, so you're given the invariant, you just want to see that it's correct. That's already something that's not, so you can't just give this format to Z3, but we actually need to come up with a way to do this counting. Okay. We give you an idea of the arguments that are being used. The first clause. So threads are at location 1. We know that the set of threads at location larger than 1 is empty, and A is bound to 0, so we have 0, and that's trivially satisfied. Okay, for the at position 2, so there's at least one element in the set, so A is bigger than 1, bigger or equal to proof. Okay. Now, perhaps the most interesting case is the inductive, and so let me show you how. bunch of threads. So some these are given by the yellow. Some of them are inside of the set, some of them are outside, and you have one particular to update, to make a transition. Just going to move inside of the set, that's it. And the change in cardinality is just you increment the cardinality of the set. Okay. Let me move on to the second question of how to. Okay. So remember we set up this system of constraints on an invariant. We gave it to the solver. But actually, you need to say, then you need to tell us, so how cardinalities you want to track. So here you want to track the cardinality by some S that the solver needs to figure out. Okay. So S and inf such that the proof goes through. Inf is cardinality free. Okay. Okay, so the way we go about this is, and we remove all occurrences of cardinalities fresh variables. See, there's no restriction on the fresh variables, so they could be recover some of the information that we lost by raising the cardinalities on cardinalities. Okay. Cardinality free and can be solved by okay, here's how this actually works on the first clause. So you say initially the invariant. What we're going to do is we're going to erase that set, and now the cardinality is just given by this unconstrained variable. To regain some information, we're instead, if the set, the predicate S that describes the set doesn't, then we know that the cardinality is going to be 0. So, so for our prior example, our solver is going to return S is going to be set to so the threads that have program counter larger than 1, and K is just smaller or equal to A. Okay. Okay, so we implemented our technique and a few protocols. So the two protocols and another locking protocol and a simple garbage collection cache about the size of the things you saw before. That it works on problem literature, and it's the first sort of proofs. Okay. Protocols, verifying protocols requires keys, and existing verifiers. So we present a method Sharpie that knows how to count and knows how to on cardinalities that are going to constrain the fresh variables. Come in.
So that's is going into the current solver.
Yeah. Mm-hmm.
Do apply to the cardinalities as well.
Mm-hmm.
Okay.
Yeah.
Thank you.
Just want to make sure that then so if verifying them, right? So if let's suppose I already have a proof, the proof is already done for finite number, or like 2 or 3. Take it and augment it basically to just extend it to arbitrary process, like garbage collection or consensus. It doesn't matter. you would want this transition somehow to. You don't want to bother with the proof for like 2 or 3 processes. To arbitrary to do that to this step or proofs are.
So for me, the basically proof for small instances and something like this shows up in choosing of saying, okay, I take one instantiate. Yeah, so by choosing that's the point where the point of correspondence. So basically, that goes into quantifier instantiation.
I see. Okay, thanks.
Hi. So Chord has a problem in its base case, and I was wondering, can your tool detect it and report, like, oh, here's the set of threads and the configuration that will cause there to be a problem? What do counter?
Did you say?
Yeah.
Okay. So
In general,
I can't really.
What do counterexamples look like? What happens when the property you want isn't true?
Okay, so how so basically, what does the of something, right? Okay, so the question is how much information you can get from. So we haven't worked too much on giving basically. So on explaining counterexamples or basically making it very making it hard easy to see what's happening. It's definitely something to work on in the future. So.
Hi. So the update actions are sound, but they are not complete. Do you have any examples where they weren't sufficient to prove the property that you were after?
So we don't have examples of incompleteness of the cardinality. So I think they're actually complete for a subfragment, but so I'd say so the focus. I mean, there is how to do the counting, and the other one is how to come up with actually what to count. I think the focus of this work is what to count, and the other problem is also in itself an unsolved or important problem, and so that said, where people ability for a fragment of the logic we are using.